speaker, Dr. Anton from Ukraine. He's going to talk about silver nanofoam as electrocatalyst for organic halide reduction.
Good morning, dear Chairman and dear colleagues. First of all, I'd like to thank you for the possibility to make this presentation on the conference. And herein, I will report the performance of silver nanofoam as electrocatalyst in reactions of electrochemical organic halides reduction. Such reactions are considered as promising tool for remediation of waste halogen organic pollutants, such as chloroform, DDT, freons, and so on, and as a tool for fine organic synthesis of valuable compounds. However, such processes undergo with high overpotentials, which is not desirable for practical use. But such overpotentials can be lowered by use of appropriate electrocatalysts. Silver cathodic materials were shown to be efficient electrocatalysts for such processes, which manifested in a significant anodic shift of potentials of such processes on silver cathode compared to inert cathode, such as glassy carbon or so. The nano-sized form of silver can be considered as further improvement of cathodic materials for such processes. However, it was shown that silver nanoparticles gave results comparable with smooth silver cathode in the reduction of benzyl chloride. Metal nanoforms can be considered as another promising kind of nano-sized materials for such applications, as they can have the same properties as than other nano-sized forms of metals, and also can inherit some properties from bulk metals. First of all, I speak about high electroconductivity. Additionally, it should be noted that nanofoam sample is one whole entity and doesn't require any binding agents or any support in principle, which is especially important if we work in non-aqueous solutions. Nanofoams can be prepared by different ways. The most promising for electrocatalysts is use of cathodic deposition under high current densities, because in such case we can obtain a readily available readily available electrode. Silver nanoforms prepared by various ways shown revealed electrocatalytic effect in a set of electrochemical reduction reactions. Some examples are present on the slide. The aim of our work was to determine characteristics of electroreduction of organic halides, a series of organic halides on silver nanoform in non-aqueous medium. Actually it was dimethylformamide, and to compare them with the appropriate characteristics of smooth silver. Silver nanofoam for this work was prepared using typical method of cathodic electrodeposition. However, we tried to optimize the composition of electrolyte used for this process. We tried to simplify it as much as possible. The nanofoam coating was formed on the surface of glassy carbon electrode as matte gray film. The chronopotentiograms of the formation processes manifested fast repeat oscillations of potential with time, which can be attributed to formation and elimination of hydrogen bubbles serving as a softer plate in this process. However, trend lines of the potentials demonstrated high reproducibility. The structure of the resulting nanoform was investigated by a series of methods. First of all, optical and scanning electron microscopy, cyclic voltammetry, and X-ray diffraction. It was shown that the resulted nanoform possess hierarchical porosity with two levels. First levels consist of craters and separated by walls. And the second level is presented by a dendritic nanocyte structure of the walls. Presence of crystalline silver was confirmed in the samples, and it was shown that electrochemically accessible surface area of this coating was approximately 8 times higher than for smooth silver of silver cathode of the same square. The silver nanoform revealed superior electrocatalytic activity in the reactions of reduction of alkyl halides, especially in the case of halothane, which manifested in anodic shift of the potential of this process on the cyclic voltammogram. The shift was about 200 of millivolts compared to the smooth silver, cathode. It should be noted, however, that a small peak at the same potentials as the process on the smooth silver cathode is presented on the cyclic voltammogram of a halothane on silver nanoform. And despite the above-mentioned difference in specific square area, the currents of the processes on the smooth silver and on silver nanoform were comparable. Such results can be explained by formation of some kind of active sites in the nanopores of the silver nanoform, which can promote the reduction of halothane more efficiently than the surface of the smooth silver. A similar situation took place in the case of dibromodifluoromethane, but in the case of this compound, the shift was significantly lower, and the potential at the peak at the potential similar to the potential of this process on smooth silver was significantly higher than in the case of halothane. We can explain such difference by a slower diffusion of halothane or by faster reduction. So in the case of halothane, it could be suggested that in the case of halothane, only the most active sites can participate in such a reaction. And in the case of dibromodifluoromethane, less active sites also take place, take part. The same situation as for alkyl halides was observed in the case of aryl halide, namely brombenzene. It should be noted that in the case of this compound, we observed the highest potential shift in the entire work, about 350 millivolts. The situation is a bit different in the case of substituted aryl halides. Contrary to the non-substituted benzyl bromide, for such compounds we can observe minor shifts of the potentials, or even no shift in the case of nitro derivative. In order to explain such difference and to find the exact description of the mechanism of reaction of these compounds, we need additional studies that will be a subject of further investigation. Comparison of cyclic voltammograms of different different samples of silver nanofoam prepared on the same method in the same conditions revealed moderate reproducibility of the characteristics of the reduction process. Despite this, we should emphasize that the superior performance over the smooth silver is statistically significant. In order to study the stability of the silver nanofoam coating in time during the reaction of organic halides reduction, we subjected the nanofoam to continuous cycling and found that electrocatalytic performance didn't degrade with cycling. However, it's true only if we steer the solution, thoroughly steer the solution between each two scans. If we subject the coating to the continuous scanning without steering, we observe irreversible in case of halocyan and or reversible in case dibromidifluoromethane degradation of electrocatalytic performance. Such difference can be explained by dissolution of possible dissolution of electrocatalytically active sites of the silver nanofoam by the products of reduction of halocyan. First of all, substituted olefins that can form in this process and can form soluble complexes with silver. Thus, we have shown the superior performance of silver nanofoam over smooth silver in processes of electrochemical reduction of organic halides and its relative stability in such processes. Thanks for your attention.
Small questions, rather. So by smooth silver, what do you exactly mean? How do you make it, what do you use for this reference? Under smooth silver, we mean regular silver cathode, regular silver electrode, so regular surface of silver. We use the term smooth silver, or it may be bulk silver, in order to make a difference between bulk metal and nanofoam. So you didn't treat it somehow, you didn't etch it before you use it or something?
We applied regular techniques of cathode preparation, cleaning, polishing with alumina and washing with isopropyl alcohol. It's regular techniques for preparation of regular silver electrode for electrochemical experiment.
Okay, and I'm also wondering, have you measured optical properties of those nanofoams?
No.
And they are black or gray?
It's matte gray. To the naked eye, it's matte gray, but we didn't measure spectra of this film.
Thank you.
We provided electrochemical measurements. We estimated the capacity of double layer from cyclic volt tomograms at different scan rates and compared it to the smooth silver surface. Now, we didn't provide another techniques such as gas volumetry. We got a small amount of this matter, so it was very difficult to make another measurements.
Question, please.